Use proportions to solve geometry problems. I want you to carefully read these two concepts. They're very, for anybody who has ever read a map, used a map to navigate, or have looked at a architectural drawing or architectural modeling, you will understand what scale drawing is, what scale is. But obviously, these are just more precise language that's used to describe these two concepts. There's no point in memorizing them as long as you understand how to use scales in scale drawing. Here's what's more important. Here are 3 additional properties of proportions. Again, you don't need to memorize them, but you should know them very, very well, to the point that you can use your own language to describe them, or I can see you're using these properties to help you solve problems in your homework and exams. Reciprocal property says if 2 ratios are equal, so if A over B equals C over D, if you just flip them on both sides, they're also equal. Look at that, B over A equals D over C. That's what, by definition, what reciprocal means, is to the numerator becomes denominator, denominator becomes numerator. If you interchange the means of a proportion, then you form another true proportion. This is probably a little bit harder to understand. Remember, the means are the ones that's in the middle. It's the B and the C, right? A and D are extremes. So the way I remember this is A over B equals C over D, but if I go this way, A over C should equal B over D, okay? And the last one says that if you add the value of each ratio's denominator, then you form another true proportion. And the examples are right here. You add B to the denominator only, to the numerator only, and then you have to add, on the right-hand side, you have to add D to it as well. So A plus B over B equals C plus D over D. Now, as part of your homework, I want you to give me examples for each of these properties. So, for example, if you give yourself an example that 2 over 3 equals 4 over 6. So if that is true, then the reciprocal property states that 3 over 2 should equal 6 over 4. And double check that, do they equal? Absolutely. You just found an example to demonstrate that reciprocal property does exist. Okay, so I want you to practice that with all 4 properties, including the cross product property of proportions that we just learned in the last unit. And for the rest of this unit is really how we use these properties to help us make our life a lot easier. So let's look at example here. It says AC at 12 over DF at 18. So AC and 18, and BC, which is 9, and this unknown X, they are proportions. So I'm going to write this out. Let's see, blue ink. AC over DF equals BC over EF. That's a proportion, which means that 12 over 18 should equal 9 over X. You can solve for X if you want. But here it's not asking us to solve for X. It's asking us to find true, right, 4 true proportions. So if I have this original right here, I can use my reciprocal property. So then DF over AC should equal EF over BC, which means 18 over 12 should equal X over 9. And or I can use interchange my means, which means that AC over BC should equal DF over EF. So that's 12 over 9 should equal 18 over x, right? And lastly, I can add the denominator. So AC plus DF over DF. Notice that I only add the denominator, but I do not change my original denominator. And then I add the denominator on the right-hand side, BC plus EF. And which means that if I do that, that's 12 plus 18 over 18 should equal 9 plus 8 over x. And so that's 30 over 18 equals 9 plus x over x. Okay, so I found 1, 2, 3, 4. That's my 4 proportions right there. In the second example, it says in this triangle JL, where's JL? JL is right here. Here is JL right here. Over LH, which is the little part there, I think that's 2, equals JK. JK is 15 over KG, which is 5. So now let's see what I can do here. If I have this is given right here, I'm asked to find JH. JH is this long length of the big triangle, and JL, which is this part, the green part. Okay, so let's see what we can do. If I use property of proportions, I can, the fourth one as they indicated here, I can add the denominator to the top. So I can have JL plus LH over LH, JK plus KG over KG. And what that gives me is the entire length of JH. I'm going to add a step here. JH over LH equals JG. Is that right? No. Equals JH over LH equals JG, that's right, over KG. And then I plug in the numbers. I should have x over 2, because x is JH, LH is 2, should equal this is 15 over 5. I'm sorry, my alignment is a little off, but you see I added an equation in the middle there. And then if I cross multiply this property, I should have 5x equals 2 times 15. That, oh, I'm sorry, that's 15 plus 5. I didn't see that. That's 15 plus 5. Right there. Now if you do your algebra, you should have x equals 8. And therefore, JH should be 8. JL should be 8 minus 2, and that should be 6. Okay? Proportions are particularly useful in triangles because, as you have learned from the previous chapters, so many information in a triangle is proportional, especially when they are somewhat similar, right? So that's often where it's used. It's a really handy tool to know all of these different properties. Here's a real life example. It says the length of the key in the scale of drawing is centimeters, 7 centimeters. So in other words, from here all the way down to here, oops, sorry, that's not quite a straight line, is it? This is 7 cm. The length of the actual key is 4 centimeters. What is the scale of drawing? So to find the scale, you have to write the equation of the length in the drawing to the actual length. So it's the drawing length to the actual length. Then rewrite the ratio so that the denominator is 1. So we said the length. Here's another real-life example. It says on this map, 1 inch to 8 miles is the proportion. Very often you find those in the legends. And you're also saying that, let's see, that's it. It's asking us to find the actual distance from Westbrook, which is right here, Westbrook, to Cooley, which is right here. Cooley is here, right here. Okay, so you have to pick up your ruler and measure the distance between the two black dots. If you do that, you will find that the distance is about 1.25 inches on this map. And the question is then, what does that represent in reality? We know that the proportion between the map and reality is 1 inch over 8 miles. That's the portion of it. And because of that, we don't have 1 inch. We have 1.25 inches. And we don't know the actual distance. So we use x to represent that. You can cross multiply by using cross product property. And if you do that, you should have 1.25 times 8. And that should give you a nice round number of 10 for x. So in this case, it's 10 miles, right? Yeah, I forgot to add, this is miles right here. So that's how we use proportion to help us solve real-life problems. Here is a very commonly used example in architecture. Here's a model. You buy a 3D scale model of the Sun Sphere in Knoxville, Tennessee. The actual building is 266 feet tall. Your model is 20 inches tall. And the diameter of the dome on your scale model is about 5.6 inches. So first question, what's the diameter of the actual stone? So you know, here's your proportion right here. You know that your model is 20 inches, and the 20 inches represents 266 feet in real life. And so you set up that ratio right there. You also know that what you have on your scale model for the dome is 5.6 inches, and you want to know the actual distance, the actual length. So that's how you set up your proportion right there. But pay special attention to the units when you deal with real life examples. It's really important that you don't mess up with the units. So here you can cross multiply. You should have, let's see, 20x, right? Is on the right hand side should be 5.6 multiplied by 266. And that should give you about, 1489.6. And if you divide that by 20, that should give you approximately 74.5. That's the diameter of the actual dome. So that answers the first question, is 74.5 feet. Second question, how many times as tall as your model is the actual building? Be careful, we have been talking about proportion for a while, but all of a sudden, when they ask how many times as tall as your model is the actual building, they're really talking about the ratio. There's no proportion in here. So with that in mind, the setup of this is simply 266 feet, which is the actual building, right? And the height of the actual building over 20 inches, which is the height of your model. And again, pay attention to your units. So once you set that up, and you have to convert your feet into inches by multiplying by 12. And, oops, and at the bottom is still 20 inches. And now you end up, I didn't write this right. To do it carefully, really, what you're doing, you're multiplying 12 inches over 1 feet. Really, you're still just multiplying by 1. But that's how you're converting the units from feet to inches, and that way you get to cancel all the units. You use your calculator, you should come up with the answer. On my calculator, it says it's 159.6. So the actual building is 159.6 times as tall as the model. Okay, so I hope this is helpful. As you can tell, there's not a lot of calculation here, but you have to understand the difference between ratios and proportions. Proportions is an equation. Ratio is simply a statement of two things and the comparison of two things. And once you have that, the rest of it is all being applied to real life. Okay, thank you guys. See you soon.